You have to cut that bird's mouth so that it planes out with the rest of the rafters on the top. We try to take the wood out of the wall and put in insulation. That changes depending on how you apply the stress in relation to the grain direction. That's right, ladies and gentlemen, you heard it here first. I'm starting off with this. We're getting right out of the gate. And I actually muted my mic this time, so we're on a roll. This is the Tower Climbers Cookbook, the best cookbook that ever existed. And you guys should get one because there are recipes in here that you cannot believe you could make for yourselves. And it's just, there's no cookbook like it. So hit me up. I've got a link in the description for my Telegram if you want to order one. Now, if you like that music because it was pretty jamming music, then you should check out the Green Observer on YouTube. He's actually in the chats today, Mr. Green Observer. Here he is. Howdy, Mr. Green Observer. Good to have you in the chats, my guy. And yes, I do believe that the stress could be calculated for the like button smashing problem. And if it could be, then I would probably like to figure it out because that's the kind of thing that I'm into. So yeah, check out his music because he makes all the music for the Bungalows for Bachelors channel, and it is all dope, every single one of them. So that is the best. That is right. And we got Mr. Will Stevenson in the chat. Hello, Mr. Will Stevenson. This is the world's best and only cookbook. That is correct. There are no other cookbooks. And so you ought to just buy this one. Otherwise, you're going to starve because you're not going to know how to cook for yourselves. So check it out, guys. Now, if you want to join the Telegram community, which is something that I've got here at Bungalows for Bachelors, you can get all kinds of good updates, posts for things going live, posts for like photos and cool stuff that's like things that come up while I'm building things, all kinds of fun stuff. We've got a good little community of people chatting around in there. So check it out. That is correct. There is no second best cookbook. Awesome. So yeah, hit that link in the description below to join the Bungalows for Bachelors Telegram. Everybody is welcome. We're all in there to learn more about residential construction and help improve. So if you want to see the body of work of all the other stuff that I do, then you can just check out my Linktree /Samuel D. Stevenson will take you there. There's also a link in the description below. And that's where I've got other stuff going on, like the Brothers Two of Them podcast with my brother Will here, who helped make me make this cookbook. And we got all kinds of other good stuff. So check it out in there. And of course, if you don't know about decentralized currency known as cryptocurrency, then you ought to check out the hex.com website, because there you can learn about the world's first decentralized certificate of deposit. That's right. You can go to not a bank, just yourself and the internet, and you can get yourself your coins and all this good stuff. And you can help save your money for the long term and like free yourself from bad decision-making skills and all of those wonderful things. So check it out, hex.com, links in the description below. Now, I've got 2 programs currently that are finished. There's a home building program, right? This is a long form content. And then there's a framing design program. That's also long form content. So I've got those 2 programs right now. I'm coming out with a home design program so you guys can learn how to design your own homes from an architectural point of view, not an engineering point of view. And I'm also coming out with the condensed home building program so that it can be a little bit shorter for you guys so you can learn a lot more efficiently. Let's get right into it, boys and girls. So today we want more. And if you don't know what the image was on the thumbnail of the Mohr, it's what's called Mohr's circle. And we're going to get into how we can basically solve all of the problems of all these crazy load combinations and everything into just what we call the principal stresses, right? And that's how we know what is like how stuff breaks, right? That's how we can design a metal angled thing that's like undergoing all kinds of loads into like one simple thing. So we just know if it breaks or doesn't, right? So it's a little complicated. I'm going to be summarizing things for you guys so that you don't have to deal with the math. And I've already done all the math beforehand. So we're going to just kind of blow right through this here. Oh man. Thank you, brother Will, for posting those links in the chat. Awesome. So let's kind of get right into it. The first thing I'm going to lead off with here is we need to understand the tensile test. Okay. So for the most part, I'm going to talk about like metals because that's what I'm talking about in my design and everything. But like it applies to plastics, it applies to kind of everything else. But metals are easy because they're fairly like consistent. So if you have a metal rod and you clamp it on the top and you clamp it on the bottom, and then you pull on it really hard, you can make it break, right? It's going to break at some point. And most people don't think about like, oh yeah, I'm like pulling a metal rod till it breaks. Like that doesn't sound like something most people do. And like that's not really a normal, like you don't think of metal objects as being pulled and breaking. Anyway, that's what we do to test them, right? It's called the tensile test. We're testing the tensile strength, aka pulling strength. The opposite of tensile would be compression. The reason we don't necessarily test compression is because like the shape of the object is going to have much more of an effect on the compressive load. It's probably going to fail by buckling before it'll fail by actual like compression failure of the molecules and atoms and stuff. So tensile testing, I'm going to upload a little video for you guys so that you can see what like this looks like. So what this is this is playing forward and backward in reverse. It's not like repeating, right? So this is a machine doing a tensile test on a piece of steel, right? It's got little marks that are showing you like where the lengths are in the piece of steel. And you can see that when it pulls on it really hard, the first part of the pull is a little slower. And then as it starts pulling really hard, it starts speeding up. And then it does what's called necking right in the middle. And what that necking is it's the material in one spot, particularly basically giving way. And that's where the fracture point is going to be. And that's just kind of what happens. So we're going to go over, the stress strain curve, quick little summary so that you guys can be familiar with like what is going on when this thing is pulling on the metal. But yeah, this is what happens. Basically, the machine's going to pull really hard. And when we do this, we can do this with all different types of alloys of steel, alloys of aluminum, you name it. Like we can pull on anything, right? If we do it for plastics, like the whole thing is going to look really different. So what's happening is there's two little arms that are grabbing the steel. And what the arms are measuring is they're measuring like displacement. They're measuring how much the thing stretches with the applied load. So there's a graph for this computer. Like the thing that's doing this is graphing on a chart how much force are we exerting to pull this thing and how far is it stretching. And with those two pieces of data, we can figure out like, well, what was the cross section of the steel when we started? And then we know the stress on the steel. We can correlate that to its deformation. And we can get all kinds of cool data about that. And that's the step we need to take with the material testing so we understand how to design something. So we get those numbers from the tensile testing. So let's just jump right in here. Give me a second while I share my screen. Let's see if I can do this well. Okay, so that's shared. Looks like everything's golden. Okay, so the stress strain diagram. So I'm going to hop in here with a marker, and it's real simple, guys. So we got a y-axis and an x-axis, and I actually ended up drawing this inverted on a previous live video, but I'm going to fix it now. On the x-axis is deformation. This is like delta distance, delta d, right? That's a terrible d, but that's okay. So that's like how much is this thing stretching, and on the y-axis is sigma. That represents the stress. Okay, so what's going to happen is as the material like is pulled, it's going to go up and up and up. And then as it's pulled, it's deforming, right? Everything deforms when it's loaded. That is just the nature. There are no perfectly non-deforming materials. If you were to look at a ceramic material, they're very brittle and very strong. They basically don't deform at all, but they do deform. And so if you were to compare like a ceramic to a steel, the chart would look something like this. It would basically go straight up, super steep, and it would just break right up here. I'd break up there. But a steel, for example, is going to do something like this. It's going to go up and it's going to be stretching out. And then at some point, it's going to hit what's called its yield point, which is where the steel no longer can flex under the load and spring back to its original position. It's actually going to start deforming. And that's where all of the crystals and all the stuff's going to start like realigning and shifting, and all of the metal is going to do its cool microstructure stuff. But basically, it's going to do something like this, and then it's going to break. Okay. And what's happening is everything up to this point was what we call elastic deformation. All right. So the material can be pulled and relaxed and pulled and relaxed, theoretically infinitely, forgetting cyclic loading. And basically the material will always continue to go back to its original position, and the material remembers no stress. Okay. If you go past that point, then you start to like permanently deform the material. And if you let go, what's actually going to happen is materials have what's called a modulus of elasticity. It's a descriptor of how bendy is this thing. And what's really cool is what happens is if you go up to like here and you deform it, the modulus of elasticity is the slope of the line at the first part, right? It's the slope of the like bending part that's elastic. And if we take that same slope and bring it back down to the bottom, there's going to be some permanent change in like length there, that permanent deformation. And that's how you can like predict that and stuff like that. So when people are forming plates or metals or whatever, and like engineers are designing, I need this 90-degree bend to come out perfectly at 90 degrees. Well, there's always going to be some elasticity in there. And so actually what the machines do is they bend it past 90 degrees and they figure out how much past 90 degrees by doing this math so that when it relaxes, it ends right where you need it to be. Long story short, this is the stress strain diagram. This is describing the loading scenarios of the like material. And like what's important about this is that you need to know that this point right here, the yield point, is what we care about. Because most of the time when we're designing and we are doing numbers with math and things like that, we don't want the steel tower holding all these things to yield. We would like it to, maybe it can flex, like that's fine. We want all of the forces and all of the stresses on this tower to like keep us in this area right here. As long as we're in that area, we can flex and we can move back, everything's fine. But we do not want to exceed the yield point there and actually deform. So that is the number we got to keep in mind, and we can go ahead and continue. So what is considered failure? It's that yield point, right? So if I make a bracket that's designed to hold a big ball and, you know, gravity's pulling the ball down, so at some point, this bracket's probably going to yield. It's going to deform right in here. And it's going to maybe like bend down like this, right? And it's not going to like that. And so we're going to define failure by that bending point. Now, how do we do that? We're going to do that by getting into what we like fancy people call finite element analysis, right? So what we're going to do is we're going to analyze elements. Here we go. First time using the online whiteboard. Okay, so the surface element is a word we give for the infinitely small patch of metal at the surface of a material. So if I were to draw a rod coming off a wall, okay, and that's the wall. this is a rod, I swear. Basically, there's a few things I could do. If I know there's some big force on the end of this rod and it's like cantilevered out and it's like trying to bend, then what I would want to do is I'd want to analyze like, okay, where's this thing going to break? Because I need to understand which infinitely small patch to analyze if I'm going to analyze a patch. Okay. So there's multiple stresses, there's multiple things going on in a situation like this, but I happen to know based on experience, and most people might be able to guess, if this is anchored to a wall, it's probably not going to break out here on the end. It's probably going to break right here at the wall on top or on bottom. And that's going to be a function of the tensile strength at that point. Because what's effectively happening is that point right here at the wall is being stretched because of the way things bend. So surface elements allow us to think about these infinitely small points as a box, right? A 2D box. So if I put a little surface patch on the side instead of on the top, I would get different like stresses based on the way things are loaded. For example, if this thing was only in bending, I would actually get no stress at the middle of the rod. There is no stress there because the top half of the rod's in tension, bottom half of the rod's in compression. Okay. So if I put a patch in the middle, then there would effectively not be any. So I'll take that patch and bring it over here. So we draw a box in 2D. There would not be any of this. There would not be no tension. There'd be no tension. There wouldn't be any compression. That's how we draw the surface element. Okay. Now the other thing the surface element can show is the other type of stress. There's either normal stress or there is shear stress. Okay. Normal stress is when something's either being like it's normal to the surface of the square here, this little thing. And shear is like a angular changing thing. So if there was a normal stress, it would look like these arrows. And if there's actually a shear stress, what it's trying to do is it's trying to take this box. It's a little bit weird to describe and take a little bit to understand the first time I learned it. But shear stress is trying to take the box and turn it into a parallelogram. That's what shear stress does. And the way we draw it usually on these rectangles is we would draw an up arrow and a this way arrow and this way and this way. Okay, so that's showing that like, hey, we're actually trying to stretch this thing in shear. We're not trying to pull or push on it. So it's kind of a weird thing to think about, but like that is what shear means. So we're going to use this little surface element patch to solve our problem. All right. And we're going to talk about one more thing before we get into our actual problem here. And before I do that, let me double check that everything's still functioning. Of course, my camera is dying. Hold on a second. Let me fix that. GPU error. Excuse the technical difficulties, ladies and gentlemen. Okay, right back into it. So I'm going to talk about this neat little thing here that happens with cyclic loads and like microfractures. So remember how I said on the stress strain diagram that things can go out and back infinitely on the yield line as long as they don't pass the yield point? Well, that's sort of true, but it's not perfectly true because things like shafts in machines that spin a lot, that undergo loads while they're spinning, are basically getting loaded and unloaded and loaded and unloaded like really fast and for a long period of time, a large quantity of times. We're talking like millions of repetitions and hundreds of millions of repetitions, right? So what happens is materials fail dynamically, is what we'd call that, by basically what we call microfractures happening at the surface. Oh, let me draw with a pen. Come on. So basically, at the surface of every material, nothing is perfectly smooth. Everything's a little bit rough. And so when something is a little bit more rough, it's going to have more natural peaks and valleys. That's what roughness literally means, right? And so what happens is if you have like a valley or something right here, right? See how this valley is just happens to dip in far? It's just because the surface is rough. Then what's going to happen is every time you load that material and then unload it, there's a tiny little crack that's going to form. And then you load it and unload it, and it's going to grow, and then it's going to grow, and then it's going to grow, and then it's going to grow until the whole thing just splits all the way through. And that's what dynamic and cyclic loading failures can cause. So the cool thing that I want to share about this is that the strength of cyclically loaded materials is a function of how smooth the material is, which is really, really interesting. On the charts when you're designing, if you have a rough material that's been like cast iron or something like that, it's going to have one factor and it's a whole other piece of data. And if you have like polished steel rods, they're going to have a much higher cyclic life because the surface is literally smooth. There's not very many places for these cracks to start forming. And so that just makes them live a lot longer. So that's just a little side note. Wanted to share that with you guys. So let's go ahead and make sure everything's still going well here. We're good. Okay. So here is the dilemma, guys. Okay. So this is my brother, Will. He's hanging out on a tower and he is leaning up against the tower with his foot. He's got a little kitty in his lap and he's in his positioner. Right. So his positioner, and notice how there's no safety. Let's fix that. The safety is hooked on up here. So in case this breaks, he's still attached. All right. I'm sure there was a safety in the real photo, but he's in this positioner and he's sitting in it and it's going up at a 45-degree angle to some bracket on the tower. And that's where he's attached. Okay. So what we're going to do here tonight is we are going to make sure that Will is safe when he hooks off into this little bracket. Okay. And what's going to happen is there's a little 1/4-inch dowel or a 1/4-inch bolt that's right where he's hooking off into. So that's he's going to load this 1/4-inch bolt. Okay. So we're going to prove with math that this is fine and he'll be okay. So what's going to happen here is we got this chart over here on the right. All right. Now we got Will weighing in at 270 pounds. And that's because he's body weight plus harness weight plus tool weight and clothes and a cat and whatever else he's got on him, bolts, hardware, you name it, right? He's coming in at 270 pounds. So that's going to be basically I'm drawing this out and I've got some angles in here just to simplify things and show what's happening. So the first thing we have is we got to break down like what's happening with the loads. Well, down here at the bottom of Will's positioner, he weighs 270 pounds, but his rope supporting him is at an angle of 45 degrees to the tower. Okay. So there's actually, I want to know the tension in the rope. I have to know what is the horizontal component of that? Well, I don't really need to know the horizontal component, but I just happen to know it's at 45 degrees. And so I just drew a little similar triangle, and we know it's, 45s are easy. We're just take 270 multiplied by the square root of 2, and we get 382 pounds. So that's what the rope is feeling. And we need to know what the rope is feeling because the rope is the thing that's connected to the bolt. Okay. So the bolt is feeling 382 pounds, pulling or pushing or whatever, right? It depends on how you draw the force diagram. But basically, that bolt's feeling 382 pounds. Now, let's see. Here's the bolt. Okay. This is a beautiful drawing of a bolt. And we are going to use 48 inch-pounds of torque to tighten down this 1/4 inch bolt. And what that's going to do with a steel bolt is it's going to provide 960 pounds of clamping force, right? So this little bolt isn't just loosey-goosey hanging out on the tower. This bolt is actually holding like some steel together, right? And it's got some washers and stuff in there, and it's got a little gap so that Will can get his hook thing in there, right? And so because the bolt is holding clamping force actively, that means the shaft of the bolt, which is the thing we are concerned with. We don't want the shaft to break when Will sits on it, right, with his load. And so we are going to have to consider the fact that not only is Will's weight going to try to shear the bolt, but the bolt is it's also being pulled by this massive clamping force. So that's a multiple loads going on at once, okay? So that's what's going on with the bolt. Now, if we simplify the bolt down into a cylinder and made it real simple, we'd say, okay, the cylinder is being pulled 960 pounds, and it's trying to be sheared by 382 pounds. And I basically just simplified the rope pulling part into just one number. It's the 382. And that's what we're trying to prove, that this thing like won't break. So we know Will's good. Okay. So the first thing we got to do is zoom out a little bit so that I can fit this all. Okay. So forces are great, but forces don't tell us much information regarding strength of materials. We need to know stresses. Okay. And stresses and strengths are listed in PSI. All right. Okay. So we're going to take, for example, we'll start with the tension. Keep it super simple. Tension in something like a rod like this is just going to be the force divided by the area. It's just like pressure, right? If you take 100 pounds and you put it on 1 square inch, then you have 100 pounds per square inch of pressure or stress being exerted on something, right? And so that's how we quantify how much the material is going, owie, this is no fun. So that's what we got going on here. It's being pulled by 960 pounds, and it's a 1/4 inch diameter bolt, right? We're assuming the threads are not being considered. It's just exactly a 1/4 inch. All right. And that's going to produce a tensile stress of 4,889 PSI. That's cool. We got one part figured out. Now we got to figure out the shear stress. Okay. And that's a little bit more complicated. We're doing transverse shear, not torsional shear. We're trying to slice the thing like scissors. We're not trying to twist it. There are multiple kinds of shear. So what it would look like is something like this, where the oh man, I'm second guessing my math here, but the math is not important. What's important is the concept. So some force creates some stress. We got this shear stress of 2,594 psi. In fact, the more I think about it, the more I don't like what I did, but that's okay. You won't know. So we have this shear stress and we have this tensile stress. So what we got going on is this little box here represents the surface element that is an infinitely small patch in the center of the rod where I think it's going to break, right? If I pull this patch from a different spot, I'm going to have to do different math, and I might get different numbers, and I might think, oh, I'm cool, I'm great, but I didn't select the part of the bolt that would actually break first. And the only reason you know which part to select is by doing this a bunch. So I'm going to pick from this side because that's where I happen to know it's going to break. And then we're going to keep going. All right. So here's what that surface element would look like with the arrows. All right. So we got being pulled apart, 4,889. And we got shear trying to deform the shape by 2,594 PSI. Okay. So this is great. This is cool, but this doesn't help us know the material. Like how, like, is this steel bolt going to break or not? Right. Well, how do we know if we're going to break or not? Well, back to that tensile test video I showed you guys. So the tensile part is important because that gives us a tensile PSI. So A36 structural steel, we're going to assume that's what they used. has a tensile yield strength of 36,000 psi. That's the number that we need to know that, like, hey, that's cool. That's the number we need. But it's like, okay, well, 4,809 psi is less than that. So it must not break, right? Well, yes and no. It's not going to break under that number. But there's also this extra stress that's going on, but it's in this shear format, which does not work for helping us understand how the material can be pulled. So what do we do about that? Well, here's what we do about that, guys. We do what's called the Mohr circle, and we're actually going to take our stress element and we're going to pivot it and analyze it as if we were like basically analyzing the stress in different directions, right? So the actual rod, the actual bolt thing, it doesn't move. It doesn't change orientation. What we're changing is our math that's analyzing it and slicing it up into pieces. So what I'm going to do is we're going to rotate our stress element, and that's going to allow us to convert the shear stress into tensile stress using Mohr's circle. You can also use equations, but it's all the same thing, basically. Okay, so this is Mohr's circle. It's a graph. It's very simple. Okay, on the x-axis is normal stress. On the y-axis is shear stress. You're going to plot 2 points. The first point is going to be x value, normal stress of the, where's my mouse? Of this guy, right? So the 4,800, blah, 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 right? And it's going to be positive because it's in tension. Negative would be compression. So the first point is going to be the x faces, and the second point is going to be the y faces, okay? So the first one has this normal stress on it. The second one has no normal stress on it. There's a zero there. There could be something squishing it from this direction or pulling it from that direction, but there's not. And then, of course, the y coordinate in both cases is going to be this 2,594. And when you basically look at the right face of this, you see that it's pulling it down. That is a clockwise rotation. And the other way is going counterclockwise. So one's going to be positive, one's going to be negative, and we're going to get this graph right here. Okay, so we get 2 points. All we do, super simple, we just connect the points with a circle. And once we have the circle is going to tell us the principal stresses in this case. The principal stresses are the place defined by where shear stress is 0. So where is shear stress 0? Well, that's anywhere that the circle hits the x-axis, right? Because that would be y equals 0, right? So if you remember your geometry. Okay, so what I need to know is maybe the point back here on the left side of the circle, or maybe the point on the right side of the circle. I happen to know that I want the point on the right side of the circle, right? Because that's farther away from the original like y-axis, and like the x-axis represents stress. And so I want to know what's the most stress. Well, that's the thing that's farther out there. So, I thought that it was experiencing this almost 5,000 psi, but because of the circle and the way I'm rotating things, I'm actually getting more where I hit out here. So when we look at the numbers, this is what happens when you look at the numbers. I don't know if it's going to be clean enough for you guys to read the numbers, but basically about 6,000 psi is the point where the circle hits the x-axis, like in terms of how far it is from the 0 point, right? So that is where shear is 0 and everything's been converted into tensile only. So I happen to know that this thing under this particular load, forgetting the part that the math is a little bit wonky, right? We have this principal stress of 6,000 psi. So we can take that 6,000 psi and notice here that there's an angle here. Because of the way the stress cube rotates, the number is cut in half for like actual rotation. So what happens is I happen to know that if I rotate the stress element 23.5 degrees, then I eliminate all of the shear stress and the only thing left is the tensile stress. That's what I know if the steel will break or not. And in this case, we know 836 is good for 36,000, and in this cube, it was only up to 6,000. So Will has a safety factor of 6, right? So he can sit down in his harness, and he is a happy camper. Look at him. He's so happy. And we know this bolt is not going to shear because we've been able to convert all the shear into tensile, and we know the tensile strength of steel. Pretty cool, guys. I think this is a pretty fantastic topic. The other way you could look at this here is that he's got a safety factor of 6, but that's assuming a static load. That means he just very gently sits down and relaxes in it, which does not happen usually. Usually it's pretty jerky, and like jerk and acceleration can cause forces to double and sometimes triple. And so What we ought to tell Will, if he's going to be climbing towers trying to sit down into 1/4 inch diameter bolts, is that he should be very careful, because if he triples his force, then he could very easily cut a safety factor in half. And let's say there was a defect on the bolt and it was weak or something, he could break the bolt. So you got to be careful, guys. But that is how that works. That is how you take something that is not tensile, make it tensile, so that we can compare to what we know about the materials. And now that we're done, we're going to go through the chats, and I'm going to catch up with what you hooligans have been up to. Oh, we got Tam in the chat. Hey, fam. Hello, Tam. How's it going? And we got Jenna Nelson. Welcome, both of you girls. Thank you for supporting the channel and learning good nerdy stuff. Let's see what else we got. We got Green Observer. I don't understand circles. I find them pointless. You are correct, sir. The only drawback is that circles do have one point, and that is at the center of the circle. But I won't call you out on that. Very good, very good. Oh, we got Tama. Sam is so smart. Thank you. Thank you. I try my best. I'm just here to share the knowledge with you guys so that you can learn and grow, and eventually maybe like go weld some plates and hang on them, and then they won't break and all that stuff. But that's what we do here at Bungalows for Bachelors. We talk about practical things that are neat and nerdy. So if you guys want to learn more, check out the rest of the YouTube stuff on the YouTube channel. You know where to find it because you're already here. And if you want to check out everything else that we got going on, check out the Bungalows for Bachelors community. All of the links are in the description below. And I will see you guys next week. I've already got the topic picked out for next week. I'm not going to let you know yet because I got to make the thing and make sure it's all going to make sense and everything. But I'm excited about it. I think it's going to be a fun one. And I hope to see you guys next week. So farewell.